Okay. So in our last class, we discussed a little bit about the basic idea for uncertainty, how the uncertainty work and such stuffs. Why do we have to deal with uncertainty? Different devices can have different type of uncertainty depending upon their precision level. How small fraction of the measurement can we do? And I told you that today I'm going to show you how to combine multiple type of uncertainties. Uncertainties calculation is actually really pretty simple. I'm going to show you some example with numbers to begin with, so that you can understand the example, and then you don't have to write anything. All of these things are well written in the printed notes, which you can collect from the which you can collect from the coaching. The booklets are prepared. I ordered, I think, 30 or 40 pieces of booklets for the first 4 chapters. You can pick it up starting from tomorrow. আর হচ্ছে ওই বুকলেট পিক করার সময় তোমরা হচ্ছে দিবা, কি বলে, অ্যাডমিশন ফি পে করবা। আর হচ্ছে এটা হচ্ছে জুন মাস, তোমরা জুলাইয়ের ফিস পে করবা। জুন মাস বাদ, জুন মাসে ক্লাস হতে থাকবে, জুন মাস নিয়ে বদলা সংখ্যা দরকার নাই। জুলাইয়ের ফিস পে করে আমি অফিসে বলে দিব, তাই অফিসের থেকেও জুলাইয়ের ফিসই রাখবে। সো এটা নিয়ে টেনশন নাই। হ্যাঁ বলো। আর ফিস কত হবে সেটার নোটিস আমি একটু পরে তোমাদেরকে লিখে দিয়ে দিচ্ছি। ওটা নোটিস বানানো আছে, I just have to take a screenshot of the PDF and give it to you in the messenger group. বলো
টাইমিংটা কি?
হ্যাঁ একজন বলো। হ্যাঁ আব্দুল্লাহ বলো, কি বলছিলা?
স্যার ওই যে সানডে টাইমিংটা আপনার ডিসকাস করার কথা ছিল।
আচ্ছা, সানডে টাইমিং নিয়ে তোমার সাথে আর বিপুর সাথে আমি ক্লাসে পরে আলাদা কথা বলবো, তোমরা একটু ক্লাসে পরে থাকো। আর হাসান বলো।
স্যার ওই যে ওই অ্যাডমিশন ফিস গুলো সব দিয়ে দিয়েছো, I don't need to visit the ELS anymore, right?
Just to pick up the booklet.
The book here, yes sir, I picked it up sir. ওটা আছে স্যার।
স্যার অ্যাডমিশন ফিস বুঝি নাই স্যার কি?
আচ্ছা, ফিস নিয়ে আমি পরে ক্লাসে পরে আলাপ করতেছি, ক্লাসটা শেষ করে নিয়ে তারপর আলাপ করতেছি। ফিসটা আমার লেখা আছে পিডিএফ থেকে, একটা স্ক্রিনশট নিয়ে তোমাদের শেয়ার দিতে হবে, ওটা এখন কাটাকাটি করতে যাচ্ছি না। হাসান, তোমার কোশ্চেনে আনসার তুমি পাই যাওয়া, ডোন্ট ওয়ারি, হাত নামাও, সমস্যা নাই, ইউল গেট ইউর আনসার ইন ডিউ টাইম, জাস্ট হোল্ড ইউর হর্সেস। Okay, so the first thing that we are going to see is that whenever we are trying to deal with multiple quantities in such a way, let's say we have a quantity x that is given by the sum of 2 quantities, let's say a plus b. Let's say let me give you an example. This can be a certain amount of time, this can be another time, this can be a certain length, this can be another length, this can be mass, this can be mass, this can be acceleration, this can be acceleration. If a certain quantity is expressed by the addition of 2 other quantities, whenever 2 quantities are to be added or subtracted, whatever it is, so I can give plus or minus over here as well, add or subtraction doesn't matter, it is imperative that both of these quantities have to be exactly same. You cannot add mass with time, you cannot add length with area, you cannot add density with heat capacity. So if you want to add 2 quantities, or if you want to subtract 1 quantity from another one, both of these quantities have to be the same quantity. That's the ground rule for addition or subtraction for 2 different quantities. So if it so happens that 2 quantities are given like this, in that case the uncertainty calculation can be very simple. Let me give some numbers. Let's say a is given by, in this case let's assume they are lengths, so let's say it is 20.0 plus or minus 0.1 centimeter, and let's say b is 13.62 plus or minus 0.1 0
টুটা কি দেওয়া যাবে স্যার?
দাঁড়াও বলতেছি, আমি এসএফ নিয়ে একটু পরে আলাপ করতেছি। লেটস সে বি হচ্ছে 0.1 millimeter and this is 13.6. Let's say these are the 2 quantities that we are provided over here, right over here. Fahim, if I understand, okay. Bumi শোনাচ্ছে, okay, hold up. এখন কি অবস্থা? Fine.
Perfect.
I just lowered it a little bit.
Yes, ঠিক আছে।
Yes, okay, fine, good. So if we have a situation where we have 2 quantities which are to be added, but we have dissimilar units, the first thing you have to do is that we have to convert them into convenient or preferable similar units. So either I can choose to convert this whole thing into say millimeter by multiplying the whole thing by 10, or I can choose to convert this one into centimeter by dividing it by 10. So let's say I'm going to convert this one. So if I divide this by 10, I'm going to get 1.36 plus or minus 0.01 centimeter. So now that I have similar units, I can now place these values over here. This is 20.0 plus or minus 0.11. Let's say first we're going to do the plus operation. So if you're doing plus, in that case, this would be 1.36 plus or minus 0.01. The whole thing comes in centimeter. Now, because we are doing addition for the time being, I mean, subtraction we simply add these two values. So we're going to get 21.36 plus or minus 0.11 centimeter. The uncertainties are simply getting added. Simply getting added because errors will always add up to give us more error. If the operation is minus, let's say if the operation is subtraction, let's say if we are trying to do a minus b, in that case we're going to write it in this fashion: 20.0 plus or minus 0.1 minus 1.36 plus or minus 0.01 centimeter. In this case, we're going to subtract these two values. However, the uncertainties will always get added. This is the important bit. The uncertainty of two different quantities, whether we add or subtract, multiply or divide, which is gonna show up in the next part of the discussion, uncertainties will always get added. So that way, in this case, if we do the subtraction, 20 minus 1.36 koto hoy? Calculator. $18.64 plus or minus 0.11 centimeter. That's how we handle the uncertainties for addition or subtraction case, which is actually quite rare. You wouldn't have to do this kind of calculation very often because it is very easy and simple, but you have to know how this works. What is important is that you might wonder that do we have to really go for this type of answers like like 4 decimal like 4 SF values, or the or do we have to go for really 2 decimal places? I mean, what is the actual standard that we have to stick to? For most of your question paper answers, the answers are mostly, let's say, I'd say 75 or 80% of the cases, the mathematical answers for uncertainty calculations, they are usually given in 2SF, not 2DP, 2SF. You have to know the difference between SF and DP. This is very important. I'm going to give you an example of SF and DP. For example, let me write a single number, 5.00 into 10 to the power 4. How many SF do you have in this expression?
3 SF, sir.
Do all of you agree?
Ji sir.
How many DPs do you have?
1, 2.
2 DP. Good. So example ta jano na keon chilo? Acha, heh. If I write a number that looks like this, how many SF is this number?
So it can be 1 SF or it can be 5 SF.
How about the in
So
between?
1 SF, sir.
Hassan, how about the in-betweens?
Sir, ওইগুলাও হতে পারে স্যার, যে একবার করছিলাম স্যার।
That is exactly the correct answer. This is what I'm trying to get at. Kids, try to understand. If you have a number that looks like this number might as well be a 1SF number. This could be a 2SF number. This could be a 3SF number. This could be a 4SF number. This could be a 5SF number. You don't know how many SF does this number have. You only see 4 zeros over here. It might so happen that whatever this measurement was obtained from, maybe that device could measure up to the unit place, but the measurement actually showed up to be exactly 50,000. It can happen. In that case, we'd say this is a 5SF number. If it was actually measured in multiples of 10, let's say you have a measuring stick of which has a total length of 10 meters. Maybe you are measuring the distance from Dhaka to Chittagong, or for one location to another location, and the length of your measuring stick is 10 meters, and there is no fraction over here. So your smallest length that you can measure is, let's say, 10 meters, and you measured the distance between 2 places and you found it to be 50,000 meters. In that case, your actual precision level starts from here. In that case, these are the SF values, so that would be a 4SF number. Having a number that appear like this can be any of these SFs, but the moment I write it in this fashion, 5.0000 into 10 to the power 4, this is a definitive 5SF number, because after decimal point, all of the things become effective SF values. If I write 5.010 into 10 to the power 4, how many SF do you think this one has?
Sir, 4.
This one has 4 SF. This is a 4 SF value. So if you have digits after the decimal point, all of the right side digits of the after the decimal point should be effective SF values. However, if you have zeros in front of the decimal places, they might be actual SF values, they might not be SF values. You do not know this for a fact unless more information is available to you. So this is really important.
স্যার এই লাস্ট পার্টটা স্যার বুঝি নাই স্যার, মানে ডেসিমাল পয়েন্টের পার্টটা স্যার।
মানে হচ্ছে মনে করো এটা হচ্ছে ডেসিমাল প্লেস, ডেসিমাল প্লেসের আগে যদি আমাদের অনেকগুলো জিরো থাকে, তারপর কোন একটা নাম্বার থাকে, লেটস সে 7 অর 8, এখন এই নাম্বারটা 1 2 3 4 5 6 7 এসএফ হতে পারে, 6 এসএফ হতে পারে, 5 এসএফ হতে পারে, 4 এসএফ হতে পারে, 3 এসএফ হতে পারে, 2 এসএফ হতে পারে, 1 এসএফ হবে না, কারণ আমার এখানে অলরেডি দুটো ডিজিট আমরা দেখতেছি। So it can be a minimum of 2 SF, it can be a maximum of 7 SF. You cannot say for sure unless you have more information available that how this measurement was done. What was the smallest measurable unit of the device that you used to get this number from whatever measurement that you did with it. So decimal point এর আগে যদি 0 থাকে সেগুলোর SF টা ডেফিনিটলি বলা যাবে না without additional information. However, decimal point এর পরে যদি 0 থাকে, ফর এক্সাম্পল যে decimal point এর পরে 0 দিছে, এখানে decimal point এর পরে এক্সট্রা কিছু ডিজিট আছে, decimal point এর পরে সবগুলা ডিজিটই irrespective of whether the number is 0 or some other actual numerical value 1 through 9, all of those things will be effective SF values. Typically তোমাদের কোশ্চেন পেপারে যে আনসারগুলো আছে, মোস্ট অফ দ্য আনসারস আর গিভেন ইন 2SF. এখন 2SF ভ্যালু যদি আমাদের হ্যান্ডেল করতে হয়, 2SF ভ্যালু আমরা অ্যাকচুয়ালি কেমনে হ্যান্ডেল করব সেটা আমি একটু পরে তোমাদেরকে দেখাচ্ছি। হাউএভার এখানে যদি আমি এই কোশ্চেনটাকে, এই আনসারটাকে যদি 2SF এ লিখি, তাহলে আমি এই আনসারটা কিভাবে লিখবো? দেখো এখানে 2SF লিখলে আমার মিনিমাম লাগবে হচ্ছে এইটুক, আমার লাগবে হচ্ছে 1 আর 8, তার মানে আমাকে 0.64 বাদ দিতে হবে। সো 0.6 এর 6টা হচ্ছে 5 এর থেকে বেশি, ইট ইজ বিগার দ্যান 5, সো দিস ইজ গোনা বিকাম 19. দ্যাটস দ্য 2SF এক্সপ্রেশন. নাও comes the question প্লাস ও মাইনাস, এখানে আমি এখন কত লিখবো? এখন তুমি দেখো 19 এর এখানে আছে হচ্ছে ইউনিট প্লেস, সো the uncertainty that you can show over here should not be more than 1 SF unit place value. So you can write only the unit place value over here. Now the unit place value for this uncertainty calculation was how much? Only 0, because if you still get rid of the additional part, you're gonna only be left with 0. So what you're gonna write 19 plus or minus 0 centimeter. If you wonder এটা লেখা ঠিক আছে কিনা, I mean is it okay to write it in this fashion, the answer is a solid yes. You can write your answer like this, because what this measurement shows us that if this quantity a minus b, which was initially x, this is measured up to 2SF, there is no error up to the unit position value. There might be error after that, but since we are not showing that value, we are not bothered about those numbers. This is expressed in the 2SF value, so I'm going to write 2SF over here. However, if I want to show this number in 3SF, let's say right over here, this is going to look like this: 18.6 plus or minus 0.
Welcome back, sir.
হ্যালো, কথা কি শোনা যাচ্ছে?
Yes, sir.
জি স্যার।
আচ্ছা, আমি
Yes, sir.
somehow disconnect হয়ে গেছিলাম, maybe a bit of a internet disruption. What I'm saying is that if we're trying to represent this number as a 3SF value, then we're going to write 18.6 over here. This is a 3SF value for the main number, and then the uncertainty should have matching DP. This is very important, matching DP. Here it was also the same. Here the final, the very rightmost decimal place was the unit position, so we have only unit position value showing up in the uncertainty value. Here for the 3SF expression of this same number, we have 18.6 because if we get rid of the 4, we don't add 1 over here, so it's only 18.6. This is the first decimal place for the main number. As a result, whenever we are showing the uncertainty over here, that number should also be given in the first decimal place, 0.1 centimeter. This is how the calculations should be done. So you can choose this number to be either 2SF or 3SF. That's somewhat within your discretion. But whatever, how you're going to represent this thing is going to be highly dependent upon the decimal places of the main number that it has depending upon your choice of 2SF or 3SF value. This is exactly how this is going to work out for pretty much every single case. Yes, Abdullah, you have a question. Bolo.
স্যার 2SF এর জন্য আমরা 0 নিলাম কেন ওটা বুঝি না স্যার
2SF এর জন্য 0 নিচ্ছি কারণ হচ্ছে if we convert this number into a 2SF number, this is becoming 19, exclusively 19, and this is the unit place. The last digit of the original number is unit place. Now if you take only the unit place for this whole value, if you take the unit place number, this is only 0 because এটা তো 5 এর থেকে বড় না, 4 বা 5 বা 5 এর থেকে বড় না, so you need to get rid of this part with mathematical round off, and ultimately you are left with only 0.
তো স্যার এমন বলতে পারি না যে যেহেতু ডেসিমাল কোন ডিপি নাই তাই আর কি 0 নিছি শুধু
না, এই নাম্বারটা যে সবসময় 0 হবে ব্যাপারটা এরকম না। এই নাম্বারটা যদি কোনো একটা সার্টেন কেসে মনে করি যদি 1 হতো তাহলে আমরা এখানে 1 লিখতাম, এই নাম্বারটা যদি 2 হতো তাহলে 2 লিখতাম, মানে we are going to match the DP of the original number with the uncertainty value. That's the core basic. Now whatever that number is, we have to represent that over here. If it is 0, you still have to show 0. That representing that 0 shows that the calculation or the measurement is accurate up to that value. There is no error up to that point, and that is an important information for measurement basics.
Yes sir, বুঝছি, thank you sir.
Sure, no problem. আচ্ছা, এটা গেল হচ্ছে একটা পার্ট, so that's for the choice of uncertainty. আর নেক্সট যে জিনিসটা আমাদের, yes বলো
স্যার।
হ্যাঁ মনে বলো।
এই তো 18.6 এর যে 0.1 করছেন এটা বুঝতে পারতেছি না কেন জানেন।
Yes sir, বুঝা যাচ্ছে না স্যার।
How many DPs do you have for this number? 1 DP. Your calculated uncertainty for right over here was 0.11. If you convert 0.11 into 1 DP value, how should this look like?
0.1.
There you are.
Okay sir.
Matching DP. এখানে যে ডিপি থাকবে এটা ডিপিটা সেম হইতে হবে, দ্যাটস দ্য বেসিক। ইসু বুঝছো?
Yes sir.
Beautiful. So if we go for the next procedure, I'm going to take some more numerical examples for the next one as well. Just have to rearrange myself a little bit. Go. So let's say a certain quantity is given as the multiple of multiple different quantities. মনে করো হচ্ছে let's say you are trying to measure the area of a certain object which is given by the multiplication of two lengths L into L. Now one of the things that you really need to understand, whenever we are doing multiplication or division to find out the uncertainty of a derived quantity, this is a derived quantity, whether these two quantities are same or different. For example, area is given by length into length, but if you are trying to get, let's say, acceleration should be given by length divided by time squared, meter per second square or centimeter per second square, whatever that is. So then again, if you are trying to get, let's say, only two multiplication, let's say Newton meter, yeah, if you're trying to measure the moment of a certain force, moment is given by force into perpendicular distance from the pivot point, so that is given by Newton multiplied by meter. So this is, in this case, we are multiplying two different values over here. Maybe we can measure the force using a spring balance, and the distance can be measured by meter rule for appropriate cases. So you can have different uncertainties for these two quantities from your measurement device, and you can have the value of the moment calculated. The information that you need to understand that whether these two quantities which you are multiplying are same or they are different, just for the case of multiplication or division to obtain a derived quantity, which is the most type of quantities that we have, there are only 7 base quantities. So most of the quantities are derived quantities for physics, for measurement process, not only for physics and for the entire world. So for those cases, we simply cannot add the uncertainty of those two quantities directly. Even if they are similar quantities, we cannot add them. For the mathematical operation of multiplication or division, we have to go through a very specific process that is called fractional uncertainty. I'm going to explain what fractional uncertainty right now. Fractional uncertainty. এখানে আমি definition related কিছু জিনিসপত্র তোমাদেরকে দেখাই। মনে করো, let's say a certain quantity, let's say P is given by this thing. Let's say কি লিখবো? আচ্ছা, P না। Let me get the example and then we can directly do that calculation for that. আচ্ছা, আমি সরাসরি একটা example লিখি। Forget about this. মনে করো, we have, let's say for a certain scenario, we have a cylindrical solid object and we are asked to measure the calculate the density of this object. To measure the density of this cylindrical body, we have some measured values which are given to us, because we are now discussing in theoretical terms, or maybe in the laboratory you have access to a top pen balance, digital balance, you have access to a micrometer, screw gauge, vernier calipers. You can use all of those devices to get the necessary data, physical dimensions and the mass measurement, and ultimately your aim is to calculate the density of the material of this cylindrical object. So let's say assume that we have this kind of data is available. Let's say the mass is given by 203 plus or minus 1 gram. The diameter of the cylinder is given as, let's say 4.3 plus or minus 0.1 centimeter. No. What is the vernier constant for a typical vernier caliper? Vernier caliper vernier constant 0.05 na?
Yes, sir.
1/20. So let's say I'm going to write this in multiple of this. Let's say this the diameter was measured to be 4.35 plus or minus 0.05 centimeter, and the height or the length, you can say length or height, however you assume it, the length I mean circle to circle face distance is measured, let's say by a meter rule, which was measured to be 5.1 plus or minus 0.1 centimeter. So our aim is to find out the density of this thing. So এটা আমরা বাই করতে হবে। এটুকু, let's say these are the values that we have calculated out from the measurement device, and now we want to go ahead and do the calculation for the density. So I'm going to show you how to do the calculation altogether. This thing is what we call absolute uncertainty, or sometimes we only say it's only uncertainty. So if I say that what is the uncertainty of the mass of the cylinder, we're going to say 1 gram. You have to mention the unit as well. You cannot only say the uncertainty is 1. You have to say 1 gram. What is the uncertainty of the diameter of the cylinder? You have to say 0.05 centimeter. What is the uncertainty of the length of the cylinder? 0.1 centimeter. So absolute uncertainty or uncertainty are mean the same thing. So I'm going to write over here absolute uncertainty. Absolute uncertainty. It comes with a value and there is a unit. Sometimes absolute uncertainty is also called just uncertainty. So if we ever mention the word uncertainty only, we have to understand that we are talking about the absolute uncertainty of the quantity. Absolute uncertainty means that there would be a measured value, which is the smallest fraction of the measuring device usually, and a unit that is added to this thing, because every measurement should have some unit, except for some very specific objects which cannot have no unit. For example, specific gravity doesn't have any unit, refractive index doesn't have any unit, angle has a value in a unit called theta, degree is basically not a unit, because you should understand that the way we define the angle for SI unit is, this is the defining equation for any angle. S equals to R, arc length equals to radius into angle measurement in radians. So if you subject the theta from this equation, you're going to get theta equals to S over R. So S is a length, R is also a length. So ultimately your units are going to get crossed out anyway. So you're not going to be left with anything else. So in practical terms, any angle value does not have any unit involved with it. So we use the term degree or we use the term radian because we want to make sense that how this was measured, whether we consider the right angle to be 90 degree and divided the whole thing in 90 pieces, that's for the degree measurement, or we want to talk about that whether we consider the entire circumference of the whole circle is 2 pi radian, and from there we can try to define the pi radian as well. But whether we write degree or radian, they do not have any SI unit convertible. There is no equivalent conversion for those two things because they are always measured as the ratio of two linear measurements. So the units cross out on the numerator and the denominator side. So there are some some quantities which do not have any unit, but most of the quantities have unit. Absolute uncertainty would mean, or normally uncertainty, if you use the term only uncertainty, it would mean that we are talking about the value, and we should also have a unit alongside that numerical value of that measurement. Then we can have, this is one type of uncertainty. Then we can have what is called fractional uncertainty. Fractional uncertainty is basically a way to represent how much portion of this measurement is errorful. For example, if I try to measure the fractional uncertainty of M, it is usually written like this. Let's say if fractional uncertainty of mass, the way we usually show this is like this: del M by M. Here the del M represents the uncertainty part and the M represents the actual value part. So this is the ratio that is what we call the fractional uncertainty. Basically, it tells us that how much portion or how much fraction of the measured quantity is actually errorful. So that thing over here is going to be 1 divided by 203. And we can write grams and grams on both sides. They're basically going to cross out each other. So to be honest, fractional uncertainty will always be a unitless number because there'll be equal same units on the numerator and the denominator side. So this is going to be a number and only a number. This is very helpful for us because this is going to prove to be really helpful for the upcoming part. I'll tell you why. You cannot add the uncertainty 1 gram with this one because this is a mass, this is a length. So dissimilar quantities, absolute uncertainties cannot be added together. However, the fractional uncertainty of a certain quantity is actually a unitless number. It is the ratio of two similar quantities. So the del M by M, the fractional uncertainty of mass, doesn't have any unit. The fractional uncertainty of diameter, del D by D, that would also not have any unit. The fractional uncertainty of length, let's say del L by L, that will also be a number without any unit. So you can logically add these numbers together because they don't have any complicacy regarding their units because the units are all cancelled out on the denominator and the numerator side. This is exactly how we combine the uncertainty information of multiple dissimilar quantities. We first get the number with the absolute uncertainty, then convert all of those uncertainty information to fractional uncertainty, which becomes a unitless fraction, just a number, just a fraction or just a number without any unit. And then logically, we can go ahead and combine these fraction values together. We can add this up together to get a total value of the uncertainty of the desired quantity, let's say in this case, which is rho or density. So that's how fractional uncertainty can prove to be very, very useful.
But sir, I didn't understand why exactly this fractional uncertainty is. I mean,
oh, this one actually shows us that how much fraction of the original measurement is errorful. For example, here it was 203 plus minus 1 gram. So the fractional uncertainty is 1 upon 203. It means for this entire measurement, 1 by 203 part can be errorful. So if you try to visualize, let's say this is the total mass of the object, and if you make 203 pieces of it, let's say this is one piece, this small fraction, let's say this is 1 upon 203 part of the whole. What this tells us that this measurement of mass can be this much more or less for the measurement equipment that we have. It tells us that how much portion of the whole measurement is errorful. I mean, one example that I can tell you that why is it helpful for us? Just a second. Yes. Okay. Yes. Okay. So another thing that I mean, why this is useful information, I mean, in its own virtue, can be said like that. In our last class, I showed you an example that if we have, if we try to measure the diameter of a certain pencil using a string, we can go around and wind a string around it multiple times. Remember? If we do not do multiple winding, if we only do one winding with the string, just that this much, and we give it a mark over here and only measure that length, and use a meter rule to measure the length of the string. Let's say this is the string and we have the 2 marks over here. In that case, if we use only one winding, then the circumference would be equals to the length plus or minus 0.2 centimeter. However, if you do 10 rotations, let's say I'm going to write that with blue, in that case the circumference would be equals to that whatever the length that you measure divided by 10, because whatever the blue length that you're going to measure, you have to divide that by 10 to get the actual circumference. Then you can get plus or minus 0.02 centimeter. So what this goes on to show you that whenever you only have one winding, your fractional uncertainty is going to be significantly large. You're going to have let me just write this as L1 and let me write this as L2. This is about nearly 10 times bigger compared to L1. So what this one shows you that this is going to be 0.2 divided by L1. So the one circumference on the denominator side, and let's say that the circumference is about, let's say the circumference is 5 centimeters. I'm just assuming this number. So what you're going to get over here, 0.2 divided by 5, this is your fractional uncertainty, which is about how much? 2 by 10, 2 by 50. That much fraction is errorful for this measurement. However, if you come to over here, if you consider the circumference to be, once again, let's say it's nearly 5, so it is 5 centimeter plus or minus 0.02 centimeter. In this case, the fractional uncertainty is going to be 0.02 divided by 5, which is going to be 2 divided by 500. So just by choosing a more repeated method, you can have a much smaller fraction of the actual measurement that is errorful. That is the physical significance of the fractional uncertainty. That tells us that how much portion or how much part of the total measurement is susceptible to error. বুঝাচ্ছে?
Yes, sir, but it also means that this is not actually the real value, right, sir?
No, this is a comparative representation for how much error is there in the measurement. This is not the actual value. The actual value would be what we call the absolute uncertainty. For example, the 0.2 centimeter or the 2 millimeter value for the meter rule. I mean, meter rule as a device has an uncertainty of 1 millimeter for one observation or one reading. That's the constant for the meter rule. But how you use the meter rule depends upon you, and that's how you can minimize the fractional uncertainty or the error amount of a certain measurement.
Yes, sir. বুঝে গেছি, sir.
মনে হয় বুঝা গেছে?
জি স্যার, বুঝতে পারছি।
আচ্ছা,
স্যার অ্যাবসলিউট
হ্যাঁ, বলো।
আনসারটা বুঝছি না।
আচ্ছা, fractional uncertainty basic concept বুঝা গেছে কিনা সবার? Anyone, if you have any question, please
জি স্যার, এটা বুঝছি।
স্যার
feel free to share. Yes, বলো।
স্যার তাহলে এটা কি এরকম যে ফ্র্যাকশনাল আনসারটি যদি বেশি হয় তাহলে এটা লাইক আমাদের আরো রিপিট করা উচিত এক্সপেরিমেন্টটাকে, আমরা কি এরকম বুঝি কিছু ফ্র্যাকশনাল আনসারের ভ্যালু দিয়ে?
Exactly. কোন একটা certain measured quantity fractional uncertainty যদি বেশি হয়, তার মানে হচ্ছে it is a bigger fraction or it has a bigger part which is errorful. So ওই কেসে I mean not essentially যে রিপিট করলে যে তোমার fractional uncertainty কমে আসবে, ব্যাপারটা এরকম না। সব এক্সপেরিমেন্ট রিপিট করলে কমে আসে এরকম না। কিছু এক্সপেরিমেন্ট আছে যে তোমার মাল্টিপল রিপিট ছাড়াও, মানে লেটস সে for example in this case having this multiple times is actually not a repetition process. You are measuring the same thing multiple times. This is very much similar like measuring the time period of a certain simple pendulum for 10 oscillations continuously without any break in between.
জি স্যার, ওইটাই। জি বুঝছি।
ঠিক আছে? সো সব এক্সপেরিমেন্টের জন্যই যে আমাদের মানে রিপিট করলে যে ফ্র্যাকশনাল আনসার্টেনিটি কমে আসবে, ব্যাপারটা এরকম না। ইট ক্যান বি স্পেসিফিক ফর experiment to experiment. It can be slightly different for different parts, but the entire idea of repeat and average is to reduce the fractional uncertainty for a certain measurement. That's the key part that I want you to understand.
বুঝছি।
Beautiful. So now let's say we want to do this whole calculation. So I'm going to dive into the calculation over here. So let's just write the definition equation for density and slowly convert the necessary values for all of these in between parts. Let's say density is given by mass over volume, mass divided by pi r square L, which is be pi m divided by pi into d by 2 d square L, and then this can be m divided by pi into d square by 4 into L. So ultimately we're gonna get 4m divided by pi d square L. Just a second, Palawan, 1 minute. Sorry, আমার ভাতিজা আয়শা আমার সাথে ভুজুং ভাজুং করতেছিল, so I had to replace him elsewhere. আচ্ছা, এই ইকুয়েশনের কনভার্সন তো বুঝা গেছে, দিস ইজ ভেরি বেসিক ম্যাথ বেস। কথা শোনা যাচ্ছে?
জি স্যার।
Yes, sir.
ঠিক আছে। সো এখন মনে করো আমরা ফার্স্ট অফ অল আমরা এই কোয়ান্টিটিটার অ্যাকচুয়াল ভ্যালুটা ডিরেক্টলি জাস্ট ভ্যালুগুলো বসা বের করে ফেলি। সো আই এম গোনা প্লেস অল দ্য ভ্যালুজ ওভার হিয়ার। আলটিমেটলি we are as the values are given to us, this is given in gram, this is in centimeter, so the length information are both given in centimeter, so we don't have to do any unit conversion. However, if it so happen that one is given in millimeter, the other one is given in centimeter, we should preferably convert all the similar type of quantities into into one type of unit. For example, all of them should be in centimeter, all of them should be in millimeter, something like that. ঠিক আছে? সো এখান থেকে যদি আমি এখন সবগুলো ভ্যালু বসাই, তাহলে আমরা বাকি ভ্যালুগুলো পাই। ফর এক্সাম্পল, let's say 4 into 203 divided by pi into 4.35 squared into 5.1. এটা ক্যালকুলেট করে দেখো যে কত হয়। I'm gonna write, because this is a working number for me, I'm gonna write a pretty large decimal place. In the very final step, I'm gonna convert this whole thing into 2SF or 3SF. But for the working value, I prefer to keep, let's say, 3-4 DPs in many cases. That's just a personal preference. You can choose to keep it less, but I would highly recommend not to stick to 2SF values for the working numbers. This is a halfway number because we're going to use this number for other calculations after a while as well. You're going to see that this is going to be a part of other calculation right after a little bit. So এটা ক্যালকুলেশন করে দেখো কত আসে। 4 into 203.
Sir, 2.67828917
আচ্ছা আচ্ছা, আমি দাঁড়াও করতেছি 1 মিনিট।
Okay, sir.
This is becoming 2.678283 লিখলেই হয়, 83 gram per cm cube. So this is our first value that we are getting for the primary value for the density. This is going to be our value of the density. Now we need to want to calculate the uncertainty of the density. We cannot directly calculate the uncertainty because we have the dependency on dissimilar quantities. So first we're going to calculate the fractional uncertainty of density. This is delta rho by rho. That would be given by the relevant fraction. So to do this carefully, I need all of you to take a good look at this expression, which is the final expression right before we place all the values. Here we have the density value is dependent upon mass. It has a power of 1. The diameter has a power of 2 and length has a power of 1. For the case of fractional uncertainty calculation, there is a bit of a logarithmic approach towards this, that how this whole thing works out. And to calculate the fractional uncertainty for multiple different fractional uncertainties, we place the power of different quantities as their multiple. So let me just write the equation and you have a look. The fractional uncertainty of density is going to be given by del m by m plus twice del d by d plus del L by L. So this square is going to show up over here as a multiple, not as a square over here. This is a logarithmic approach. You don't have the exact explanation why this comes as a multiple from the power, but if you want to look it up, you can. I can direct you to the necessary documentation, which is a bit far-fetched for your syllabus level. It's not introduced in your syllabus level. You just have to know that the power comes as the multiple. Sometimes it can also happen for some certain calculation. You can also have the fractional power. For example, if I just give you an example, let me write over here. Let's say you have a sphere, you have a spherical object, and you are told that this is a uniform sphere, so it has a same radius in all direction. You are asked to calculate the radius of the sphere, but you don't have any length measurement device. You are allowed to use a measuring cylinder to measure the volume. So you can measure the volume, and from the volume you are asked to calculate the radius. So it is possible to calculate that way, because we know that the sphere volume the volume of sphere is given by the formula 4/3 pi r cube. এই ফর্মুলা তো চিনো সবাই, চিনো?
জি
জি স্যার।
ঠিক আছে। সো এখান থেকে যদি আমি এখান থেকে r কে সাবমিট করি, what I'm gonna get 3v divided by 4 pi to the power 1/3, right? এটা পাবো না? তো এখানে দেখো 3/4 pi যে পার্টটুকু, এই ফ্র্যাকশনটুকু হচ্ছে প্র্যাকটিক্যালি একটা কনস্ট্যান্ট. This whole thing is a constant. It doesn't have any uncertainty over here because these are just numbers and a constant. So whenever we're going to do the fractional uncertainty of radius for this equation, if you're doing our calculation, in this case del r by r should be equals to 1/3 of del v by v. So whatever your fractional uncertainty that you get from the measuring cylinder, your fractional uncertainty for radius should be 1/3 of that, because volume has a power of 1/3 on top of it. So what about the power? That one should come out as the multiple in front of it. That power could be an integer value, that can be a fractional value, it can be anything, but that simply comes up in the front as a multiple for the fractional uncertainty calculation. এই পার্টটা বুঝা গেছে?
জি
Yes, sir.
জি স্যার বুঝছি।
সো এখানে আমরা এখন তাহলে ভ্যালুগুলো আস্তে আস্তে বসাই, ভ্যালুগুলো বসাই দেখি যে আমাদের ক্যালকুলেশনের ভ্যালু কত আসছে। del m by m should be 1/230, sorry 230 তো না 203, ভ্যালুগুলো গেল কই? 2 পরে, okay, I'm actually running out of space. Acha, I can zoom out a little bit. 1/203 plus twice 0.05 divided by 4.35 plus 0.1 divided by 5.1. So এখান থেকে ক্যালকুলেশন করে দেখো যে এই পুরো নাম্বারটা কত আসে। You can get this in a decimal fraction. I really don't mind. It doesn't have to show up as a fraction, because we have decimals and fractions, everything merged up together. Just put it in a calculator and see how much you get.
Sir, 48.1 into 10 to the power -3.
Sir, I got 164 divided by 3451.
Yeah, in fraction this is actually 164 divided by 3451. Yes, if you are absolutely correct. And if I want to get this into decimal, this is 0.0 90118806. It goes on further. These are the 10 digits that is available to me for me on the calculator. Anyway, I'm going to use this fractional uncertainty as which is the answer of the calculator. So I'm going to use that memory for my upcoming calculation. So, or if you want, you can use the whole fraction number over here. It's not essential that you have to keep it in the whole fraction. Benefit of having the whole fraction is that you can avoid round of error at the end of your result. Sometimes that can prove to be significantly large if you are not very careful. So now what I need I need all of you to understand one thing. This is the fractional uncertainty of the density quantity, which means this fraction shows us how much part of this number is the uncertainty. So if I just write it over here, have a look how this is happening. Delta rho by rho is given by 164 divided by 3451. So if I want to calculate the delta rho, which is the absolute uncertainty of rho, this should be 164 divided by 3451 multiplied by rho. I just cross multiplied it, only this part. So I'm going to place this value over here. So 164 divided by 3451 multiplied by 2.6783. So gram per cm cube. So that's basically your total calculation. And if you just do the multiplication right here, use the answer value of your thing. So I'm gonna keep the AC. Don't give on. So I have the answer multiplied by 2.6783. This gives me 0.2414 gram per cm cube. Do all of us have the same number? Hello? Okay, mute হয়ে গেছি?
না স্যার করতেছি।
আমার 0.127 আসে।
সেম
জি
স্যার
স্যার আমারও স্যার।
স্যার ওই 164/3451 ওইটা ডেসিমাল ভ্যালুটা মিলে না।
0.04 সামথিং হবে ফ্র্যাকশনটা।
স্যার আমার 0.127 মানে 279
তাহলে কি আমি ভুল করছি কোথাও? দাঁড়াও আমি কি ভুল করছি দেখি।
ফ্র্যাকশনের ডেসিমাল ভ্যালুটা
164 divided by 3451. আচ্ছা এটা লিখতে ভুল করছি আমি, দাঁড়াও ফ্র্যাকশনটা লিখতে ভুল করছি। (0.90118806) 0.90। আচ্ছা এটা অ্যাকচুয়ালি লিখতে ভুল করছি। I forgot. I messed up this ratio. Forget about this thing. Use this number everywhere. 0.90. So 0.090 118806 multiplied by 2.6783. 0.2414 তো আসে।
স্যার ফ্র্যাকশনের ভ্যালুটা কি হবে তাহলে?
না এখানে ফ্র্যাকশন লেখার দরকার নাই। আমি ফ্র্যাকশনটা ক্যারি আউট করতেছিলাম জাস্ট ফর আ মোর অ্যাকুরেট রেজাল্ট। You don't have to carry out the fraction. You can choose to write either this or this. You don't have to write both of them. In most cases, this is a preferable number. You can choose not to write this whole thing. You can choose to write this thing up to only 4 dp or 3 dp. But I recommend that you use the answer of your calculator for the next multiplication. So you write answer multiplied by 2.6783 so that you get this whole number. I'm getting this exact number.
Sir, what I meant was আমরা এই ভ্যালুটা কিভাবে পাচ্ছি স্যার?
কোনটা এইটা?
হ্যাঁ স্যার, fractional uncertainty value.
এই জিনিসটা, this is the fractional uncertainty value. So this is the value of delta rho by rho, which is, so let me just erase and write for you so that you can see it. So forget about this fraction value. আচ্ছা এটা মুছা যাচ্ছে না কেন? I don't know. Delta rho by rho is equals to 0.090118806. So rho equals to হচ্ছে this same number multiplied by rho, ঠিক না?
স্যার
আমার ডেল্টা রো বাই রো 0.047 আসছিল।
yes sir 0.04752 2245
ক্যালকুলেশন ভুল করছে
স্যার
1
জি
ভাগ
স্যার
203 এত প্লাস 2 into bracket 0.05 divided by 4.35 plus bracket 0.1 ভাগ 5.1 আচ্ছা হ্যাঁ আমি এখানে একটা ভুল করছি আমার এই নাম্বারটাই ভুল আসছে তাই না
জি স্যার ফ্র্যাকশনটা ঠিক ছিল
ফ্র্যাকশনটা ঠিক ছিল নাম্বারটা ভুল আসছে
জাস্ট সাচ এ ডাম পারসন আচ্ছা ঠিক আছে আমি পুরোটা কারেক্ট করে লিখতেছি আবার সরি আমি তাড়াহুড়া করতে গিয়ে ভুল করছি এন্ড আলটিমেটলি তাড়াহুড়ার বেনিফিট পাচ্ছি সেটা হচ্ছে আরো দেরি হইতেছে সেটা হচ্ছে 0.047522457 সো এটাকে আমি যদি ডেসিমেলে নেই তাহলে আসে হচ্ছে 164 ডিভাইড বাই 3451 আচ্ছা ঠিক আছে সো এখানে আমি লিখি ধরো এই ডেল্টা রো বাই রোটা হচ্ছে এই নাম্বারটা ঠিক আছে সো আমি যদি শুধু ডেল্টা রোটা ক্যালকুলেট করতে চাই তাহলে কি হবে এই নাম্বার মাল্টিপ্লাইড বাই রো এর ভ্যালুটা আসবে ঠিক না
Yes, sir.
খেয়াল করো কারণ রো এর ভ্যালুটা তো অলরেডি আমি ক্যালকুলেট করে ফেলছি করছি না এই যে রো ডেনসিটির যে অরিজিনাল নাম্বারটা আমার এই পুরো এফোর্টটুকু কি করার জন্য এই পুরো এফোর্টটুকু হচ্ছে আমার যে আনসার এই যে রো এর ভ্যালুতে যে একটা মেইন নাম্বার থাকবে প্লাস ও মাইনাস যে আরেকটা ভ্যালু থাকবে এটা বের করার জন্য আমার এই পুরো এফোর্টটা হচ্ছে আনসার্টেনিটি বের করার জন্য আমার অ্যাকচুয়াল ডেনসিটি ক্যালকুলেশন তো এইটুকুতে হয়ে গেছে আমি ভ্যালুগুলো বসাইছি ডেনসিটি তো অলরেডি ক্যালকুলেট করে ফেলছি so up till this point my density calculation is done but I am doing all of this effort to calculate the uncertainty of the density so I first calculate the fractional uncertainty because through the pathway of fractional uncertainty I could combine the individual uncertainty information of dissimilar quantities by converting them all into ratios so I did that and calculate the fractional uncertainty and then from using the fractional uncertainty I'm trying to get the absolute uncertainty which is the delta rho so I'm just multiplying this number by row I'm just basically taking this over here multiplying both sides by the row symbol so this is becoming 164 divided by 3451 multiplied by this density 2.6783 এখন দেখো বুঝা যাচ্ছে কিনা
হ্যাঁ স্যার বুঝাচ্ছে
or if it helps better I could write that this fraction of this one or so this much fraction of the original density that's more understandable I think for the key definition of the fractional uncertainty if that helps so if you do the multiplication we're gonna get to this number so this is basically our fractional uncertainty so ultimately if we're trying to write the answer first I'm going to write a big answer then I'm going to convert it into the numerical answer so 2.6783 plus or minus 0.2414 এই পুরোটুকু হচ্ছে আমার আনসার্টেনটি ক্যালকুলেটেড আনসার এখন আমি যদি এই পুরো আনসারটাকে 2SF এ কনভার্ট করতে চাই লেটস সি ইফ আই ওয়ান্ট টু কনভার্ট দিস ইনটু 2SF I'm going to write 2.7 2SF plus or minus 0.2 gram per cm cube
স্যার
if I want to just a second if I want to convert this into 3SF I'm going to write 2.68 plus or minus 0.24 gram per cm cube বলো
স্যার যে ভ্যালুটা তো ভুল ছিল
0.1273 আছে
crap আচ্ছা মনে করো এই ভ্যালুটা কারেক্ট আছে ডিসরিগার্ড দ্যাট এটা কত ছিল 0.
1273
0.1273
আচ্ছা ঠিক আছে আমি কারেক্ট করে লিখতেছি আবার বলো তো
1273
0.73 so let's say 0.1273 so এটা হবে হচ্ছে 0.1 এটা হবে হচ্ছে 0.13 দেখো ক্যালকুলেশনের আনসারটা বোঝা যাচ্ছে কিনা this is how
Yes,
we
sir.
work for dissimilar quantities whenever we have a ratio based equation Anyone? Any question? I could call out names, but I really don't want to call out names. But we have a lot of people over here who have been all quiet since the very beginning. Either it's making sense or it's not making sense. You can ask your question in the chat window. You can ask your question in the voice channel. However, or you just raise your hand. I'll help you. I'll try to help you.
স্যার আনসার কি সবসময় 2SF লিখতে হবে এগুলোর জন্য?
That's your choice. I personally prefer 3SF values all through the answer paper. That's a personal choice. But CAE CAE says that the entire paper should be preferably in 2SF or in 3SF. Students should not mix up SFs within a single question. What I'm trying to say is that, let's say you have a certain question, SF, you have a certain question which has, let's say, 2 or 3 numerical answers to be given for a certain question. You should not mix up SFs of a single question. Let's say if you write, let's say 2A1 in 2SF and then give 2A2 in 3SF and the other one in another DP, that kind of mix up is prohibited. You're going to lose marks for that. But I recommend that the final answers, you from this point onwards, you either stick to a 2SF practice all the way through your AS course for all the answers, or you go for a 3SF value. There is a rule of thumb that how much SF should we give for a certain number, which I'm going to show you right now from a practical guide advanced skills paper. There is a certain rule of thumb that how many SF should we choose. There, I'm going to show this to you right now. But before I show you about the preference of SF calculation, is this calculation understood properly by everyone? এটা মুখস্থ করা লাগবে না, বুঝলেই হবে যে কিভাবে হচ্ছে। এখানে মেইন বোঝার জিনিসটা হচ্ছে যে ডিসিমিলার কোয়ান্টিটিজ এর আনসার্টেনিটি গুলো অ্যাড করা যাবে না, because they are different quantities. You cannot add mass with time or length with density or something like that. So the only possible way that we can merge the uncertainties of dissimilar quantities is by converting all of them into fractional uncertainties. That becomes a number without units, and then we can multiply the power of those relevant quantities in front of them, and we add all the fractional uncertainties, and then from the fractional uncertainty we can very easily calculate the absolute uncertainty of the quantity. So এটা নিয়ে আমি তোমাদেরকে কিছু আরেকটা ম্যাথ দেখাই, আমার নোটসে আরেকটা ম্যাথ করা আছে. Let me just try to find that out.
Uncertainty will always be less than 1, right?
No. Fractional uncertainty typically is always less than 1. Fractional uncertainty typically is always less than 1 because it is, আমি বলতেছি মনে করো হচ্ছে fractional uncertainty কেন less than 1 হবে. It is not recommended that we measure an object with a measuring instrument that has an uncertainty that is bigger than the length of the object. For example, you cannot use a meter rule to measure the thickness of a hair. That would be highly, what can I say, like dumb.
Erroneous, yes.
Yeah, it would be dumb, simply. So in that, so if someone does it and come up with a certain number, let's say they use, I mean, I don't know how is that even possible, but let's say someone mistakenly does it. In that case, the fractional uncertainty can be more than 1 because the uncertainty would be bigger than the actual measured quantity, which is not supposed to happen. A choice of that kind of measurement value and that kind of equipment would be a wrong thing to do to begin with. Fractional uncertainty should be as much as possible. The smaller you can make it, either through the choice of a measurement device or through the choice of a measurement technique, the more small you can make it, we say the better your results are, the more accurate your results are.
Sir, এটা কি বলা যায়, like if you're measuring a meter rule, they are measuring the distance between meter division, like like 160 kilometers, তাহলে percentage uncertainty or fractional uncertainty অনেক high হবে.
একবার বলো, আস্তে আস্তে বলো।
স্যার, যদি একটা মিটার রুল দিয়ে অনেক বড় একটা ডিসটেন্স মেজার করি, like 160 kilometers or something, তাহলে percentage like fractional uncertainty, can it be greater than 1 then?
In that case, the fractional uncertainty will be pretty small, not big, because it will be 160 kilometer plus or minus 1 meter, right? So if you convert 160 kilometer to meters, that is 160,000 meter plus or minus 1 meter. So the fractional uncertainty will be 1 divided by 160,000. So if you use a small step size to measure a large quantity, that's actually what we want to do. In that case, our fractional uncertainty will be quite small, and that's preferred.
Yes, sir.
Beautiful. আচ্ছা, তোমাদেরকে যেটা দেখাতে চাইছিলাম, এক্সাম্পল দেখাই।
আজকে যে ক্যামেরা অফ,
বুঝি নাই।
আজকে যে ক্যামেরা অফ।
আচ্ছা গরম বেশি, খালি গায়ে ক্লাস করাচ্ছি তাই।
ও
এগুলা কি আমাদের এই ইয়াতে ওয়ার্কশিট মানে ওয়ার্কশিটের সাথে দিয়ে দিবেন নাকি?
হ্যাঁ এগুলো সব ওয়ার্কশিটের সাথে ইনক্লুডেড যাবে, এগুলো সব পাবা। আচ্ছা এখানে প্রিসিশন আর অ্যাকুরেসি আমি এখনো তোমাদেরকে বলি নাই। প্রিসিশন অ্যাকুরেসি আমি এখনই কথা বলা শুরু করব। আগে তোমাদেরকে যেহেতু আনসারিক ক্যালকুলেশন পড়ালাম, আনসারিক ক্যালকুলেশন নিয়ে কিছু দেখাই, ইউনিট কনভার্সন নিয়ে কথা বলছি। আচ্ছা এখানে আমি আনসারিক ক্যালকুলেশনের আরেকটা পার্ট তোমাদেরকে বলতে ভুলে গেছি, এটা আমি সবসময় ক্লাসে বলতে ভুলে যাই, পরে মনে হয়। সেটা হচ্ছে এখানে একটা জিনিস লিখি, আমি রেড দিয়ে গ্রিন দিয়ে লিখি। আনসার্টেনটি একটা এক্সপ্রেশন হচ্ছে অ্যাবসলিউট আনসার্টেনটি, আর একটা এক্সপ্রেশন হচ্ছে ফ্র্যাকশনাল আনসার্টেনটি। থার্ড একটা এক্সপ্রেশন আছে যেটাকে আমরা বলি হচ্ছে পার্সেন্টেজ আনসার্টেনটি। ওইটা হচ্ছে ফ্র্যাকশনাল আনসার্টেনটি ইনটু 100%। মানে বেসিক্যালি এই ফ্র্যাকশন এটা যদি 100% দিয়ে মাল্টিপ্লাই করো তাহলে আমরা বলবো এটা হচ্ছে ম্যাসের পার্সেন্টেজ আনসার্টেনটি। ফ্র্যাকশনাল আনসার্টেনটি মাল্টিপ্লাই বাই 100%, any fractional uncertainty multiplied by 100% gives you a number that is called percentage uncertainty. It's just another way of expression because sometimes we prefer to have a visualization in terms of 100 parts. That's the whole idea of percentage, that if you convert something into percentage, it tells you that within 100 part, how much small is that. So sometimes it's easier for us to comprehend for us human beings. এখানে আচ্ছা এখানে আমি আরেকটা জিনিস দেখাই। ফর এক্সাম্পল এই যে এখানে একটা জিনিস খেয়াল করো, লেটস সে when multiple quantities are added or subtracted to get a final quantity with relevant coefficients, essentially all of these are same quantity, so uncertainties get added to relevant coefficients. এটা মানে হচ্ছে লেটস সে p is a quantity that is given by x plus p is a quantity that is measured as x plus minus delta x unit. এখানে আমরা ইউনিট কথাটা লিখছি because I did not use numbers over here. I'm just trying to show you that this is a certain measured quantity and q is a certain measured quantity. They might be same, they might be different, we don't know yet. But let's say if r is a new quantity which is represented as 2p plus 3q, so there are some multiples over here. In that case, the calculated value of r would be 2x plus 3y plus or minus 2 into delta x plus 3 into delta y. You're simply going to add all the uncertainties with the relevant coefficient of these things to get the total uncertainty of this thing. এটা হচ্ছে যদি আমাদের প্লাস ও মাইনাস হয়। আর যদি সাবট্রাকশন হয় সেম থিং, মেইন কোয়ান্টিটিটা ক্যালকুলেট করার জন্য টু ক্যালকুলেট দ্য মেইন পার্ট of the r prime, which is a different quantity than r because it is shown as subtraction, we're simply going to do the subtraction over here. However, uncertainty parts would always get added because more errors will always create bigger amount of error. Errors are not considered to be self-compensating by their own virtue, so errors or uncertainties are always added. সো এটা হচ্ছে একটা পার্ট। এখানে তোমাদের মাল্টিপলের পার্টটুকু আছে, যে মাল্টিপলের পার্টটা আমি অ্যাকচুয়ালি লেকচার পার্টে দেখাতে ভুলে গেছিলাম, বাট উই হ্যাভ দ্য নোট, সো ইটস অ্যাকচুয়ালি কভারড।
স্যার
ইয়েস বলো।
স্যার এখানে তো জাস্ট অ্যাড অর সাবট্রাক্ট হলো, কিন্তু স্যার আপনি যে ডেনসিটিটা দেখালেন ওখানে তো ডিভিশন ছিল না।
এই যে এখানে আসতেছে নাম্বার 2টা দেখো, for product or division of multiple quantities similar or dissimilar, we cannot directly add some uncertainties. Rather, we have to calculate fractional uncertainty of all the given quantities and then add the fractional uncertainties with the power of quantity in equation as coefficient of fractional uncertainty. এই সেন্টেন্সটা বুঝো। Rather, we have to calculate the fractional uncertainty of all the given quantities, then add the fractional uncertainties with the power of the quantity in equation as coefficient of the fractional uncertainty. This is possible because fractional uncertainty do not have units. Lastly, absolute uncertainty of the m quantity is calculated using total fractional uncertainty. So এখানে ওই এক্সাম্পলটা আছে যে ডেনসিটি ক্যালকুলেশন করে, এখানে different numbers আছে because I was working with different number over here. So mass is given, length is given, here the diameter was given. So we plan to calculate the density in gram per centimeter cube. First thing, convert everything in m units. So here I gave the diameter in millimeters, where I gave the length in centimeters. So they had to convert the diameter into centimeter first, and then the equation showed up and we calculate the gram per cm cube, and then the density fractional uncertainty equation that I showed you. Here I wrote the relevant parts of the values that I gave for that class. These are just random numbers generated from my brain, so they can be different. And then we have the value of the fractional uncertainty, and now we have the absolute uncertainty of the density is given by that fractional uncertainty multiplied by the density value, which was 41.948. So 41.948 over here is multiplied with the fractional uncertainty value. You can see over here that I also asked the students to maintain a big number, a long number so that we have less problem with rounding of error at the end of the math. So 41.948 is the density over here, and the fractional absolute uncertainty is this much. And then you have the gram per cm cube values over here. That's basically your absolute uncertainty, and finally we write the answer. So there are multiple ways we can write the answer. This is shown over here. So density is written over here as 41.9 plus or minus 0.8 gram per second. This is a 3SF value, and the uncertainty is given as the matching decimal place with the original number. If we want to go for percentage uncertainty expression, this is a new part which I didn't discuss. So a part ta khayal karo. Zoom in a little bit. Yes. If you go for percentage uncertainty expression, percentage uncertainty of rho equals to delta rho by rho into 100%, which would be this number 0.7935 divided by this number, the actual value of density 41.948, this ratio multiplied by 100%. So we got 1.8916%. What do we need to say over here? That so density can be expressed as either 41.9 plus or minus 1.89%, এই পুরোটুকু ব্র্যাকেটের ভিতরে গ্রাম পার সিএম কিউব। আমরা পার্সেন্টেজ আনসারটি এইভাবে দেখাতে পারি, অথবা আমরা অরিজিনাল নাম্বারটার সাথে ইউনিটটা দিতে পারি 41.9 গ্রাম পার সিএম কিউব, দেন উই ক্যান অনলি রাইট প্লাস অর মাইনাস 1.89%। দুইটা এক্সপ্রেশনই ইকুয়ালি অ্যাকসেপ্টেবল, বাট দুইটাকে মেস আপ করা যাবে না। ইউ ক্যানট রাইট পার্সেন্টেজের পরে আবার আলাদা করে গ্রাম পার সিএম কিউব লিখতে পারবে না। সো দিস হোল নাম্বার affected by the percentage uncertainty plus minus পুরোটার ইউনিট হচ্ছে গ্রাম পার সিএম কিউব, অথবা the main unit is given as gram per cm cube plus or minus 1.8. These are the two different ways to write the appropriate thing. Have a look at the NB. When writing the final answer with absolute uncertainty, we must give the value in 3SF. This is my personal preference, but in many cases you can also come across 2SF value. So don't consider this as a must. I would more say that you should. Must is a more emphasized version, I think. Match the 10 to the power x for both value and absolute uncertainty. এই জিনিসটা আমি তোমাদেরকে এখনো দেখাই নাই। Match the 10 to the power x for both value and absolute uncertainty. এই জিনিসটা কি সেটা আমি একটু পর দেখাবো whenever we're going to work with some more small numbers. So this is going to show up. Give matching dp of absolute uncertainty with value and give correct unit. To express the final answer in percent uncertainty, both value and percent uncertainty number are given in 3SF. So you can see over here that if this is given in 3SF, this is also given in 3SF. If we wanted to write this number into 2SF, we could have written 42 gram per cm cube plus or minus 1.9%. That would also be an okay answer given in 2SF. Everything is given into 2SF. Whenever the percentage uncertainty is given, we match the SF. Whenever the absolute uncertainty is given, we match the DP. Take this out. 41.9 plus or minus 0.8. What is matched over here?
Sir, DP.
DP. 41.9 plus or minus 1.89%. What is matched over here?
Significant figure.
Significant figure. এই জিনিসটা খেয়াল করতে হবে যে পার্সেন্ট আনসারটি দেওয়ার সময় আমরা এসএফটা ম্যাচ করি, আর যদি অ্যাবসলিউট আনসারটি ম্যাচ করি সেক্ষেত্রে আমরা ডিপিটা ম্যাচ করি। এটা কেন এভাবে করতে, এটা করার বেসিক কারণটা হচ্ছে যে whenever we give the absolute uncertainty with the matching DP, it means that we have mentioned the original number up to a certain decimal place, and the absolute uncertainty is also given up to that decimal place, which means that I am not implying that this uncertainty is going to affect this number beyond what we have shown. I have shown this number up to 1 dp over here, so 41.9 up to the first decimal place. So my absolute uncertainty is also given for the first decimal place, so that this 0.8 will affect it in the this original number in the first decimal place. So I don't want to get bothered over the later digits, because I did not mention those digits means I do not want to affect those values either. Up to the precision value that I have shown, I should give my absolute uncertainty up to that number, so that it is easily workable, and that's the standard way to represent this fractional uncertainties. That's why we have to match the DPs whenever we give the absolute uncertainty. But for the case of fractional percent uncertainty, we usually go for equal SF. That's the typical norm. 10 to the power 10 এর পাওয়ার ম্যাচিং এর জিনিসটা আমি তোমাদেরকে একটা एग्जांपल দিয়ে দেখাচ্ছি এখন। Let me just pick up some numbers. Let's say I'm just gonna come up with some number. Let's say a certain quantity, let's say R, is calculated to be 3.24 into our GT 2456 into 10 to the power minus 9. Let's say, what unit should I give? Unit. And let's say after calculation, after going through the whole process of fractional uncertainty calculation, ultimately we calculate that the uncertainty of this quantity, absolute uncertainty of this quantity was measured to be 1.67325 into 10 to the power minus 11 unit. So আমাদের ক্যালকুলেটর থেকে এই দুটো নাম্বার বের হইছে। Is it possible? বুঝো, একটা সার্টেন কোয়ান্টিটি আমরা ক্যালকুলেট করে বের করছি এত, আর ফ্র্যাকশনাল আনসারটেনিটি ক্যালকুলেট করে সেটা ফ্র্যাকশনাল আনসারটেনিটি আলটিমেটলি আমরা কোয়ান্টিটিটা অ্যাবসলিউট আনসারটেনিটি বের করছি হচ্ছে এত। এরকম দুইটা ভ্যালু হওয়া পসিবল কিনা? অবশ্যই আমাদের অ্যাবসলিউট আনসারটেনিটি কি হবে, মেইন কোয়ান্টিটি থেকে সাইজ ছোট হবে, which is okay. This 10 to the power minus 9, this 10 to the power minus 11. Are we okay with this?
Yes, sir.
ঠিক আছে, মনে করো একটা সার্টেন ক্যালকুলেশন থেকে এরকম দুটো নাম্বার আসছে। নাও if we are try to represent combine these two information within a single sentence, and if we want to represent this whole thing in a single number, the first thing we have to do, we have to make sure that both of these numbers have the same 10 power. This original number has a power of 10 to the power minus 9, so I'm gonna prefer, I could do the other way around as well, but in this case, first of all, I'm going to show you the other way around as well. I'm going to convert this into 10 to the power minus 9. So if I want to convert this to 10 to the power minus 9, what should happen? The decimal place should move two places on the left, right? So this is going to look like what? 0.1, 0.01, 0.0167325. ঠিক না?
Yes.
So now I should write unit. So now I can write the final answer, that quantity R can be given as, let's say 3.2456 plus or minus 0.0167325 whole bracket into 10 to the power minus 9 and then unit. This is how you have to deal with numbers which has a power of 10. Now you don't ever have to write this long number. I'm just showing you this long number to give you an idea that how this should be working. You can directly choose to write this into 2SF. For example, if we just look at this number, if I want to write this into 3SF expression, this can be 3.25 plus or minus 2 decimal place, so 0.02 into 10 to the power minus 9 unit. এটা হচ্ছে প্রসেস, বুঝা গেছে?
বুঝছি স্যার।
ঠিক আছে, এটা হচ্ছে একটা জিনিস। অল্টারনেটলি আমি যদি এইটার পাওয়ারকে ফিক্স রেখে এটার পাওয়ারকে চেঞ্জ করতে চাইতাম, সেক্ষেত্রে আমি চেঞ্জ করতে, ফর এক্সাম্পল আই কুড হ্যাভ রিটেন দিস থিং লাইক দিস 324.56 into 10 to the power minus 11, এটা আমি করতে পারি। সেই কেসে আমার ফাইনাল আনসার কুড বি অলসো রিটেন লাইক দিস 325, I'm adding 3SF value, so 325 plus or minus 2, because 1.67, so if I take the unit place, this is 2 into 10 to the power minus 11 unit. এটাও লিখা possible, but typically we don't do this. This is uncommon to change the power of the main number. We usually keep the main original number quantity in standard form, that is something point something 10 to the power something. We preferably keep this in the standard form and prefer to alter the tens power of the uncertainty. So this is the more common practice. However, although this is quite uncommon, but this is not mathematically wrong. So if in some cases, especially in the MCQ papers, this kind of expression shows up, you cannot say this is actually wrong. This is common, this is uncommon, but both of them are mathematically correct. এই 10 এর পাওয়ারের ব্যাপারটা বুঝা গেছে কিনা সবার ক্লিয়ারলি?
Yes sir.
Yes sir.
অল রাইট, আরেকটা জিনিস যেটা তোমাদেরকে দেখাতে চাইছিলাম সেটা দেখাবো। আচ্ছা, আমার এখানে কি বের হয়ে আছে ইউটিউবে? গিফট কার্ড
স্যার বেসিক্যালি দুটোর রেজাল্ট সেমই হবে নাকি?
হ্যাঁ, দুটো রেজাল্টই সেম, ম্যাথমেটিক্যালি দুটো আইডেন্টিক্যাল থিং, বাট ওয়ান হ্যাজ মোর prominence than the other. Acha, there is a third way to calculate the uncertainty for whenever we have operators. Operators je jinishta ki seta ekটু pore boltechi, but before that let me just show you one থিং, সেটা হচ্ছে ইয়াতে আছে, কোথায় আছে, এটা আছে হচ্ছে পেপার 4 এর, না পেপার 4 না, ল্যাবের ইনস্ট্রাকশন পেপারে, হেলথ ম্যাটেরিয়ালস ল্যাবের ইনস্ট্রাকশনটা কই জানো, best practical guide. Yes, that's the name. Where is the best practical guide? Paper 3. Best practical guide. Right. Got it. Best practical guide. What is really wondrous is that if you look in the internet, best you're gonna get that. There it is. Best practical guide. So if you just download this, you're gonna get that. Anyway, I can share this PDF with you. No big deal. Here you have a huge detailed way for how to handle the lab proceedings. So I usually give always give this PDF as an introductory material for the paper 3 practice, which I'm gonna share this way with you without any backlash. No big deal. What I want to show you is the way how many about the relevance for SFs. So this is actually ways to go for this. খেয়াল করো, significant figures. Many candidates use an appropriate number of significant figures in a calculated quantity, but often do not understand why. In their explanation, it is expected that the number of significant figures in the final calculated quantity will be related to the number of significant figures in the raw data which has been used in the calculation. You need to understand that how the SF of your final answer is affected by the inside values of the equation that you obtain using your measuring instruments, which we call raw data. Raw data are measured from the apparatus table, and calculated data are calculated using the raw data. For example, for the example that we just did in this case, the density was the calculated data, and the mass, the diameter, the length, these were raw data. So we need to make sense that how the raw data affects the SF of a calculated number. Have a look. Common errors made by weaker candidates include vague statements such as it increases the accuracy of the experiment. You cannot say that. This is actually about question number 2. In question number 2, you have to give a validation for the choice of your SF. And then I'm going to plot a graph. So I'll give my answer to 2 significant figures. This is not a valid reason. Confusion between the significant figures and decimal places. For example, I have given x to 2 decimal places, so x should be given to 2 decimal places. There is no such rule like that. এখানে একটা জিনিস বলে দেওয়া আছে, দাঁড়াও।
স্যার র ডাটা কোনগুলো বললেন একটু?
এক মিনিট, আচ্ছা আমি পুরো প্যারাগ্রাফটা পড়ে যাই। র ডাটা হচ্ছে এক্সপেরিমেন্ট টেবিল থেকে আমরা যে ডেটাগুলো মেজার করে বের করে আনি, using a meter rule, using an ammeter, voltmeter, multimeter, using a mass balance, or using a spring balance. Anything that you measure using a measuring equipment is called a raw data. Time measured using stopwatch, like that. মানে মেজারিং ডিভাইসের গায়ের থেকে যে জিনিসটা এক্সট্রাক্ট করা হয় সেটা হচ্ছে র ডেটা। পরে ওই র ডাটা ইউজ করে যেগুলো ক্যালকুলেট করি সেগুলো হচ্ছে ডিরাইভড ডেটা অর ক্যালকুলেটেড ডেটা। আচ্ছা, এই জিনিসটা খেয়াল করো। Here we are trying to calculate the values of x cubes where we have some values available for x. The x values are all given for 3SF, but the x cubes were given into 5SF. This is wrong representation. A 3SF data cannot logically give you dependable 3SF 5SF value. So you cannot have more SF. Clearly, both set of values of x cube and x and s cube are given to two decimal places. However, values of x cube are given to 5 significant figures, which is not justified from the position of the values of x. Changing the third significant figure in the value of for x 2, 3, or 4 changes the third significant figure in the values of x cube 7, 8, 9. This is what they are trying to say. Have a look. 6, not select, no. Zoom in, have a look. The first SF of this number is 6, the second SF is 5, and these two numbers are same for all of these three examples. What we should see that for these numbers as well, the first SF is 2, the second SF is also 7. So variation of the value of x on the third significant figure is actually bringing in the changes 7, 8, and 9. So what they are saying that changing the third significant figure of the value for x 2, 3, or 4, these are the 2, 3, or 4, changes the third significant figure in the values of x cube 7, 8, and 9. Hence, the values of x for x cube should only be quoted to 3 significant figures to be consistent with the values of x from which they were derived. So this is a logical representation that why we should have similar SF whenever one data is used to calculate a further set of data. Why should we stick to SF, not DP? There is a certain rule of thumb which is somewhere within this paper, but I cannot find it right now. But I can just show this to you, and it will be part of the video. Anytime you need this to get this, you can actually find it out. Let me just show you this thing. In my given data for this example, all of our data, 2 of our data were given into 2SF, 3SF, and 1 of our data was given into 2SF. Have a look. This data is given into how many SF? Mass?
3.
This is 3SF data. This is
3.
This one?
2.
Good. The way final calculation should look like, the rule of thumb is that I'm going to write this over here. পড়ো কি লিখছি? Calculated final value should be expressed as the smallest SF of all the raw data. So if you're doing a calculation using 3 numbers and they have dissimilar SFs in their raw values, the one that has the smallest SF, final answer should be given in that SF. The reason behind it is like this. This number is true up to the second significant figure. This number is given up to 3 significant figures. So this number can be also considered to be true up to at least 2 SF. This number can be also considered to be true up to 2 SF. So all of these 3 numbers are all together in generally correct up to 2 SF. So the final answer should be also correct up to 2 SF. That's the logic behind it. However, CIE also allows, I don't know the reason, I honestly don't know the reason, but I know that they allow, CIE also allows the smallest SF of the raw data plus one more SF. So if the smallest SF is actually in this case 2, you can actually give the answer of this whole math into 2 SF being the smallest of the SFs of the raw value, or 2 plus 1 is 3. You can also give them into 3 SF as well, that they will also accept that. However, let's say if a certain quantity, let me give you an example. Let's say x was calculated as a cube, b to the power 4, c to the power 2/3, something like this. And let's say a is given as 1, 2, 3, 4 plus or minus not 5, or let's say 1 unit. B is given as 2, 3, 5, 0 plus or minus 5 unit, whereas C is given as 2.3 plus or minus 0.1 unit. Try to have a look at it. Here I have intentionally made a significant difference of SFs. So this number is given in 4 SF. This number is also given in 4 SF. However, this number is given into how many SFs?
2.
2.
2 SF. By this logic, the X should be given into how many SFs? How many SFs should be acceptable?
2.
2.
2 SF, which is the from the smallest, or CA also accepts which one?
3.
2
3.
plus 1 SF. ঠিক আছে? এই নাম্বারটা আরো বেশি থাকতো। For example, I could have written 1, 2, 3, 4.5, 0.1.5. In that case, this number would have been a 5 SF number. Still, the acceptable SF for all of this number, for this value of X, should be equal to the smallest SF value of all the raw data, or the smallest SF value of the raw data plus 1. You can give one more extra SF for the final answer. That's the logic that is accepted for your syllabus version. এইটা তোমাদের ল্যাবে কাজে দিবে এবং হচ্ছে whenever you are confused that how many SF should I give for a certain calculation value, you can always take this rule and this will always pay off in the long run. এই ইনফরমেশনটা এই পিডিএফ এর কোন এক জায়গাতে আছে, আমি পুরোটা পড়তে যাচ্ছি না, বাট আমি ভুলে গেছি কোথায় আছে, কারণ অনেকদিন ধরে এটা পড়া হচ্ছে না, প্লাস গত বছর ল্যাব করা নেই, সো মাই ব্রেন ইজ ব্ল্যাঙ্ক. I'm going to find this out on my own time. I'll also share the PDF with you. You can have a look at it over here. This is a very good guide for the lab practices. I'm going to explain in detail for this entire PDF for all of you in one of your theoretical classes to have you better guidance in the lab proceedings anyway. আচ্ছা, কি দেখাইতেছিলাম জানো? নোটস এ ফেরত যাও। আচ্ছা, there is a third way for which you can calculate the uncertainty, and this is the third way if we have operator. আচ্ছা, operator পার্টটা আমি বুঝাচ্ছি. I'm going to take a small break, 3-4 minutes break. বলবান আসতেছি, একটু বসো. So how can we calculate the uncertainty for certain quantities where we have some operators? Now, what are operators? Operators are mathematical operations which converts a certain quantity into a unitless number. For example, let me write you an equation. Let's say refractive index equals to sine I by sine R. This is a known equation for you. I and R are the two quantities which are measured in degrees for incident angle and refraction angle, and n is the refractive index. So whenever you convert the sine I, you get a unitless number. Sine R gives a unitless number. I and sine I are not the same thing. They are totally different. This operation changes this property in a different way. If it was cos, it changes a different way. If it was tan, it changes a different way. If you have a certain quantity, let's say X, that you have measured out of a measuring instrument, maybe time, maybe length, maybe volume. If in any case you do log of that quantity, you basically have something of a number. You can do log of 1000 or maybe 1020, but you cannot do log of 1020 meter. The unit is not taken into account whenever we use the operator with a certain measured quantity. So these are the things that we call operators. Similarly, if you place a certain quantity as power, let's say a certain quantity, let's say, is given by where 2 to the power x. X is the measured quantity out of your experiment, but it is coming as the power of a certain base number, maybe a constant. Or it can also be possible, let's say a certain quantity, let's say P is given by x to the power y. X is a measured quantity, y is also a measured quantity. Now in this case, x is a value which will not remain as x once it is taken to the power of y. So in this kind of cases, we cannot go for the fractional uncertainty thing that I just showed you. For these kind of scenarios where a certain measured quantity is used with an operator or with an operator function, we have to use a different method, third different way to measure the uncertainty. Now, interesting factor, this third method that I'm about to show you, however, is practically applicable for all sorts of uncertainty calculation, which can prove to be very useful in your A2 syllabus paper 5, যেটা আমি ওই সময় তোমাদেরকে আবার আলাদা করে দেখাবো, বাট ফর দ্য টাইমিং আমি এই এক্সাম্পলটা তোমাদেরকে পিডিএফ থেকে দেখাই, তাহলে আমার লেখা কম লাগবে। মনে করো কোন একটা সার্টেন কেসে measuring the refractive index of a transparent material measured or given, I is given as 57 degree plus or minus 2 degree, and reflection angle is given by 37 degree plus or minus 2 degree. Now you might wonder, why 2 degree, why not 1 degree? Because there is a reason. Try to understand this thing. Whenever we measure any angle using a protractor, how do we measure that angle? Let's say we have an angle that this is our normal, this is our surface, let's say this is the incident angle. To measure the incident angle, you are going to place your protractor across this thing. You're going to place your protractor like this, right? And you're going to measure this much angle. To measure this angle, you are making actually two observations. First, you're going to observe this 0, 0 line to become aligned with the protractor 0, and you're going to see the observation over here. So to be able to measure this whole angle, you are actually making two observations. The smallest division of a protractor for your protractors, the small protractors, is 1 degree, because you are making two observations to measure one angle. So here you have a plus minus uncertainty of 1 degree. Here you have a plus minus uncertainty of 1 degree. So the entire angle, let's say I, will have a plus minus of 2 degree. That's why the 2 degree comes in. If the protractor was even bigger, let's say you have a really big protractor where the borders, where the smallest fraction of the degree values are, let's say, half degrees. In that case, your uncertainty can be measured into plus or minus 1 degree, because half degree for one element, half degree for the other element, together they give one degree. So because you have to make two observations, that's why the actual uncertainty of the measured quantity is double compared to the smallest fraction of the device. এই জিনিসটা কি বুঝছো?
জি স্যার।
দুটো অবজারভেশন ব্যাপারটা বুঝা গেছে কিনা?
ওইটা বুঝছি।
ঠিক আছে। সো মনে করো আমরা এই দুটো ভ্যালু পাইলাম, এখন আমরা এই দুটো ভ্যালু দিয়ে আমরা এখন রিফ্রেক্টিভ ইন্ডেক্স ক্যালকুলেট করব। রিফ্রেক্টিভ ইন্ডেক্সের বেসিক ফর্মুলা খুব সিম্পল, n = sin i by sin r. সো প্রাইমারিলি আমরা দুটো ভ্যালু ডিরেক্টলি বসালাম, we place all the values of I and R, the very basic values 57 and 37. We calculate the refractive index. I have written this number up to 4 decimal places for convenience's sake. Then we have to calculate the possible maximum and minimum value of n depending upon this fraction's behavior. This is really important. I'm saying the term this fraction's behavior. I'm going to explain in detail after a while, but for the time, try to understand this. The way sign fraction works is this. Let me show you. Within the variation of I value from 0 degree through 90 degree, sin I versus I has an increasing relationship. As I increases, sin I also increases. Not in the linear pattern, because এটার ভ্যালু হচ্ছে 0 থেকে 1, ম্যাক্সিমাম হচ্ছে 1, আর এটার ভ্যালু হচ্ছে 0 ডিগ্রি থেকে 90 degree. So as I increases, sin I also increases. So a bigger value of I gives you a bigger value of sin I. Rule of thumb for the range of 0 to 90 degree. This is how sine ratio works, but that's not the case for cosine. How does the cosine ratio works for the same range? If you are ever measuring cos I by I, that ratio would be like this, right? At 0 degree mark you have 1, whereas as the 90 degree mark you have 0. So cosine ratio behaves the opposite way compared to sine ratio, that as the value of angle increases, the cosine ratio value actually decreases. So because of that, they don't behave the same way. So you have to understand the way how this fraction is affected by the I to be able to apply this third method. So have a look over here. If you're trying to want to measure the maximum value of n, the numerator has to be biggest and the denominator has to be smallest. So we are making this I value the biggest, 57 plus 2 degree, because the value of I was given as 57 plus minus 2 degree. So the biggest angle of I can be 57 plus 2, and the smallest value of R can be 35 minus 2, because I want to have the smallest value in the denominator and the biggest value on the numerator to get the maximum value of n, and that's the maximum value of n possible out of the total range of I and R that we have measured. Similarly, the minimum value of n should be sine 57 minus 2 degree divided by sine 35 plus 2 degree, which gives us this value. So these are the two terminal values of n max and n minimum. Then we have to do the uncertainty calculation by the difference divided by 2. Now, why the difference divided by 2? Let me explain that. Let me give you a number line. Let's say this is a number line that goes out all the way up. Let's say this is our 0. This is the negative side. We don't have to bother about negative side. Let's say a certain number is measured to be 1.6. Let's say, which has an uncertainty of how much? Let's say plus or minus 0.2, which means this number's actual value is considered to be 1.6. We can have an error of 0.2 over here, figure not drawn to scale. So this much is 0.2 on the plus side. This much is also, let's say, 0.2 on the minus side. So this is 1.6, exactly 1.6. This is the upper limit, this is the lower limit. So if you know this is the maximum value of this quantity, let's say if this number is x, so in this case I can say that the value, maximum value of x should be how much? 1.6 plus 0.2, which is 1.8. Similarly, what should be the minimum value of x? 1.6 minus 0.2, which is 1.4. Now what I need you to understand, if I do the difference between the maximum and the minimum, x max minus x minimum, within this gap, how many uncertainties do you have? Take a look. One on the right, one on the left, right? Check it out.
0.4.
So you have one delta x over here, you have another delta x over here. So the difference of the maximum and minimum practically gives you twice the uncertainty of delta x. So if you want to subtract delta x, you get the maximum minus minimum divided by 2. That's the whole idea of why we have to do it divided by 2. If you somehow can find out the maximum possible value of a certain number and the minimum possible value of a certain quantity, and then you want to calculate the uncertainty, you have to find out the difference and divide that by 2 to get the actual absolute uncertainty. That's exactly what we're doing over here. So we do this and then divide by 2. So the delta n, this was supposed to be delta. It's a bit, I think, messed up from the scanning or something. So this was meant to be delta n. Delta n equals to 0.10635. Now we're going to write the final answer. So the n was calculated to be 1.46. So if we go for a 3SF expression, n equals to 1.3. If you wonder why 3SF is acceptable, because have a look here, the angles were given up to how many SF? 2SF, right? Both of the angles were given in
Yes, sir.
2SF. So the final answer can be either given into 2SF or 2 plus 1 SF. So we can stick to 3SF value, which is perfectly okay by the logic. So reference is finally given by 1.46 plus or minus 0.11. So this is 0.11 because we want to give up to 2 decimal places. This has to be matching with decimal places. So this is up to this much we want to keep on the left. So the 6 is getting added to the 0. So that's why it is becoming 0.11. That's the final expression.
Sir.
Now, hold your horses. Now, what is really important that if in any case you have a different expression, you have to use your brain to choose the maximum minimum value. For example, let me show you a certain ratio with cosine. Let's say for the same values, let's say I equals to 57 plus minus, was it 57 and 35?
Yes.
57 plus minus 2 degree. And let's say R was 35 plus minus 2 degree. Let's say a certain ratio, whatever that ratio is, let's say X is given by cos I divided by sine R. Now, if you want to measure the delta X of this thing, then you have to be careful to choose your addition or subtraction. For example, if you're trying to get the maximum value of X, you need to have the biggest value of numerator. Now, the way cosine behaves, which I showed you on the graph over here, where is the graph? Here is the graph. The way cosine behaves is that smaller angle gives you a bigger value, right? Within the range of 0 through 90. Take a look. The class time is nearly over. Yes. I'm just gonna finish this part and we're gonna call it a day. So the way the cosine ratio works is that for a smaller value close to 0, within the range of 0 to 90, you have a bigger value of cosine. So if you are trying to get maximum value of x on the numerator side, if you want to get a big fraction, this needs to be 57 minus 2, because the smaller angle is going to give you a bigger cosine fraction value. And on the denominator side, you need a small value of sine as well. So this is going to become sine of 35 minus 2 as well, because you are trying to get the maximum value of x, which means this has to be very large, this has to be very small. The way these two fractions behave is that we need to have a subtraction for the cosine ratio for a big value of cosine value, and we have to do a subtraction of the sine ratio angle so that we have a small value of the sine value. Now this is going to give you the x max value. In the vice versa way, if you want to try to find out the x minimum, উপরে হবে হচ্ছে addition to give a small numerator, and নিচে হবে হচ্ছে subtraction. So নিচে হবে addition to give us a large value of sine, so that the ratio is the small. So that's how you have to use your idea of mathematics to get the appropriate expression of maximum and minimum. The maximum minimum is never a rule of thumb যে numerator side সব সময় add হবে, denominator side সব সময় subtraction হবে. No, you have to use your concept of mathematics to understand that how can we make for the maximum value, the numerator has to be very large, denominator has to be pretty small. For the minimum, the numerator has to be quite small as possible, and the denominator needs to be pretty large as possible. So you have to use your mathematical knowledge carefully to choose where we should add and where we should subtract. বলো
স্যার আমি আমরা ডিভাইড বাই 2 করলাম কেন এটা বুঝি না।
ডিভাইড বাই 2 করছি তার কারণ হচ্ছে এই জিনিসটা খেয়াল করো, এখানে আমি যে एग्जांपल দেখাচ্ছিলাম, মনে করো হচ্ছে x এর ভ্যালু হচ্ছে 1.6 and it has an আনসারটি of 0.2. সো আমি যদি নাম্বার লাইনে দেখাই, মনে করো এখান থেকে a2 পর্যন্ত হচ্ছে 1.6, এই যে a2 পর্যন্ত 1.6, এরপরে 0.2 হচ্ছে তার পজিটিভ সাইজের একটা আনসার্টেনিটি, নেগেটিভ সাইডে একটা 0.2 আনসার্টেনিটি আছে। সো এটা হচ্ছে আমার x এর ম্যাক্সিমাম ভ্যালু, which is 1.6 plus 0.2, which is 1.8, আর এটার বামের ভ্যালুটা হচ্ছে 1.6 minus 0.2, which is 1.4. So if you look at the difference of these two ranges, how many delta x do you have within this range?
0.4 মানে
that is, you have two delta x, one on the right side of 1.6, one on the left side of the 1.6, right?
Yes sir.
So the difference between x max minus x minimum basically gives you twice the delta x.
বুঝছি স্যার, বুঝছি।
Beautiful. Any further question?
না স্যার, আমি পার্টটা এখনো ক্লিয়ার হয়নি স্যার।
কোন পার্টটা
মানে
বুঝছেন?
স্যার টুয়াইস দ্য ডেল্টা এক্স কিভাবে হয় স্যার?
Have a look on the number line. This is your midpoint. This is
Yes,
1
sir.
delta x on the right side. That is 1.6 plus minus 0.2 na. This means what? 1.6
Yes sir.
plus 0.2 or 1.6 minus 0.2. তাই না?
Yes sir.
This is the maximum value, the positive range. Here you have 1 delta x over here and one uncertainty. And on the negative side, you have another uncertainty. So if you find out the difference of this whole thing, this whole part, you have how many 0.2s over here?
2 sir.
2.
Oh.
So the difference of these two ranges gives you double of the uncertainty value. That's why ultimately if you divide the difference by 2, you get the absolute uncertainty right of the equation.
Achha sir, I understand why we divide by 2, but sir, why do we subtract? Why not add?
Addition is gonna give you, if you do the addition, and then if the average of these two number 1.8 plus 1.4 divided by 2 is basically gonna give you the midpoint. We already know the midpoint.
Oh, then
We are trying to find out the uncertainty. That's the effort is for.
Okay sir.
Okay. So এটা হচ্ছে third procedure, and that's basically it. In your next class, I'm gonna help you understand the ideas about precision and accuracy. That's a new thing for us, and that's a bit of a theoretical concept where you have to basically look at a single value of data or a group of data and be able to pick up a decision that whether they are precise or accurate. Precision and accuracy do not mean the same thing. You have to understand the difference of these two definitions, and I'm going to help you about those things in the next class. So আজকের ক্লাস এই পর্যন্ত শেষ, আমি রেকর্ডিং স্টপ করতেছি। এরপর আমি তোমাদের সাথে ইয়া নিয়ে আলাপ করবো, কি বলে এই ফিজ নিয়ে আলাপ
টাইমিং
করবো।